Hey physics, let's look at Newton's second law. So about unbalanced forces and acceleration. So Newton's first law of motion is about inertia. So it says that objects have a tendency to resist a change in motion. If they are moving, they want to keep moving at a consistent pace. If they're holding still, they want to keep holding still, as we can all relate to, right? So you can think about it like this. Here's like a flow chart of how this all works. So if forces are balanced, even if the thing is already moving, if forces are balanced, then that means there's going to be no acceleration. And that means that either the velocity or the object is at rest and it's not moving at all, or that the object is in motion, so its velocity is not 0 meters per second, but it's going to be a consistent velocity. So object at rest will stay at rest, object in motion will stay in motion. Newton's second law says that the presence of an unbalanced force is going to accelerate an object, changing its speed, its direction, or its speed and direction. So you can think about, right now these bags on this camel are balanced, but if there was more force on one side than the other, that could tip it over. If the camel pulls in one direction, it's going to change the direction, accelerate it in a different direction. If this person is holding still, but that wind rushes into her umbrella, that's going to give an unbalanced force to her and cause her to move in one direction or another. So you can think about that like this. If forces are unbalanced, then there is an acceleration in one direction or another. But how much acceleration depends on the net force applied, how much force, and that's a direct relationship. More force equals more acceleration, and the object's mass has an inverse relationship with that. So more mass equals less acceleration. Again, you can think about this camel pulling this stuff, and it could go a lot faster if it wasn't having to carry so much mass, right? So that's what that one's about. More force, more acceleration, less force, less. So a direct relationship, inverse relationship. All right, so there's an equation that we can use to figure out about either the amount of acceleration, the amount of net force, or the amount of mass. And it goes like this. Acceleration is equal to the net force on the object divided by the mass of the object. And we have a triangle for that. So you can solve for acceleration by doing the net force divided by the mass, or you can solve for the mass by doing the net force divided by the acceleration, or you can solve for the net force by doing mass times acceleration. Also, you can graph this. So let's look at a variety of different graphs here and see how they're going to look as we're doing them. So I have also made a video of myself going through each one of these with car noises and everything. It's really great. I think you're going to like it. But I'll kind of like briefly go through this right here with you. So when velocity is a straight line, that means that there's no acceleration. It's kind of like, it's similar to a position time graph where there's no movement, right? Well, this is like no change in velocity. So you can be going forward at a consistent pace, or if you have a negative velocity, you could be going backwards at a consistent pace. But basically, there's no change in acceleration when that velocity value is flat, basically. When there is acceleration and deceleration, you're going to get a slope on a graph like this. So again, this is velocity on the y-axis instead of position. So how much is the speed changing over time? And I want you to recognize that when velocity is 0, that means that there is no velocity. There is no movement there. But when you get higher above 0 or lower above 0, that means that there's more and more movement that way, meaning you're going faster and faster as you get farther away from 0. So if we look at 6, for example, so 6 and 9 are both starting off at 0 miles per hour, 0 meters per second, and as time goes by, they're getting faster. The difference being that 6 is getting faster in the positive direction, away from the starting point, forward, and 9 is getting faster in the backwards direction, in the negative direction. So you could think about it like they're both starting right here, and as time goes by, they're going faster and faster away from that same starting point. Whereas 7 and 9 do the opposite thing. They are starting fast, and they're slowing down as they're getting closer to 0. And really, this isn't telling us about their position at all. It's just telling us how fast they're going over time. So you can think about it like they're going fast and then slowing down, okay? Both of those in both directions, okay? And we're going to practice that some more today during class. So let's do 3 practice problems real quick here. So here's a free body diagram of we're going to calculate what net force is needed to accelerate a car that is 1,500 kilograms at 3.0 meters per second squared. So I'm going to put this up here. I'm going to move this over. Okay, so basically here we have, we want this car to go forward at 3.0 meters per second. So that's our acceleration. This is our mass. So using this triangle here, we are calculating the net force, F net. And if you want to make it look fancy, you can make this in smaller font. F net equals mass times acceleration. So the mass is 1,500 kilograms. And so I guess I'll just write mass times acceleration. Okay, so that's going to be F net equals 1,500 kilograms times 3.0 kilograms, or sorry, meters per second squared. And again, to get that square, there's some kind of like function plus that somebody told me about today, but there's also, you can go to insert, special characters, type in sup, which means superscript, and press that 2 there, meters per second squared. Okay, so 1,500 times 3 is going to be 1,500 times 3. 4,500 newtons of force. Okay. Just going to make it look nice. Okay, there we go. 4,500 newtons. So then, so for this one, if we were going to draw a graph of this, then, actually, let me just add that slide. So instead of drawing a graph, we're going to find which graph it would look like of the example graphs that we have. So this car is accelerating forward at 3.0 meters per second squared. So it's not going to be a flat line one because it is accelerating, and it's accelerating forward. So I'm going to say this is going to be like number 6, accelerating in a positive direction. Okay, so now let's look at this one. A 7.3 kilogram bowling ball rolls down a ramp with a net force of 20 newtons of downward force acting on it. What is its acceleration? So this time we're solving for acceleration, so I'm going to do acceleration equals the net force divided by the mass. A equals F net divided by mass. And I'm going to make that small. Okay, so that's going to be A equals the net force is 20 newtons divided by 7.3 kilograms. So that is going to be 20 divided by 7.3 is going to be, and again, when you see a big number like this, just don't worry about the rest of these numbers. Like, I see that the numbers in the problem here are like 7.3. It goes to the 10th place. So just go to the 10th place here. So this is going to be 2.7. 2.7 meters per second squared. 2.7 meters per second squared. Okay. And last practice problem. Oh, and this one. Oh, so this is a good question. what would the graph look like for this one? So this is a 7.3 kilogram bowling ball rolling down a ramp. So my initial thought is it going to be this one because it's rolling down a ramp? But no, right? Because this graph is not talking about position, it's talking about velocity. So this one is also going to be acceleration, right? It's starting at 0 meters per second as it's at the top of a hill, and it is accelerating, we could say in a positive direction, or we could call it this one if we are talking about a downward force being like a negative acceleration in the downward position, perhaps. So then, Mrs. Allen is pushing a box with a force of 12 newtons. Friction is acting against the motion with a force of 5 newtons. If the box accelerates at 3.5 meters per second, what is the mass of the box? So, we are solving for the mass, but first we have to figure out what the net force is, because we have two different forces here. So, we have 12 newtons going in one direction. Let's see if I can click on my text box up here. Yes, I can. There it is. Okay. So I have 12 newtons in this direction, and I have 5 newtons in this direction. So, oops, my screen moved there. So 12 minus 5 is going to be 7 newtons. Okay, so now that I know what my net force is, now I can do this thing here. So, I'm solving for mass of the box. Okay, so I'm going to do net force divided by acceleration. So, mass equals F net divided by acceleration. Okay. There. All right, so let's put our numbers in. So we have the net force is 7 newtons. 7 newtons divided by 3.5 meters per second squared. And I bet you guys can do this math in your head, figure out what this is. Meters per second squared. Soup. Okay, so the mass is going to be 2 kilograms. Okay, and those are our practice problems, or the example problems. We're going to do some more review of graphs first thing, and then we're going to do a bunch of practice problems. Okay, so I'll see you guys today. Bye.